Welcome to the course on FPGA based signal processing systems. We are going to do the timing analysis for the combinational and sequential logic circuits what we had developed as a part of the synthesis process. After synthesis, where the next step which we come across in the Verilog module, which needs to be dumped into the FPGA, has this timing parameter details and timing analysis. So before getting this code, after synthesizing, then dumping into the code, that before going to the timing analysis process of the codes what we had developed, need to know the timing parameters involved in this combinational and sequential logic. So in the combination logics, like this arithmetic basics what we learned of the adders circuit and the multipliers, those things, in that what is the propagation delay involved in the, if it is in the gate level, also the critical path which needs to be identified for the each circuit, it should be known. Apart from that, what are the sequential delays? Sequential elements has some of the parameters associated with that, as propagation delays of TPLH and TPHL and so on. So let's see that what are the timing parameters here. So there is one first thing we can say, that it is a rise time of this every gate logic gate undergoes an input to output change, whereas the input is changing from 0 to 1. Similarly, the output would change if it is a not gate, then high to low or 1 to 0. So in that case, what is the rise time measured for that case? The time which is required for the signal to make transition from 10 to 90% of its maximum value, that is 0.1 of the maximum to 0.9 to maximum, how much time the signal transition takes, that's the rise time. And then the fall time is that similarly from the high to low, that is 90% of the maximum value to the 10% of the maximum value is what is the time it takes for the signal transition. So this is 0.9 of this maximum value to the 0.1 of the maximum value, how much time it gets to transit from 0.9 to 0.1. So that is termed as fall time, TF. And the propagation delays involved are TPLH and TPHL. So the delay is between the 50% of the input change to the same thing which is achieved in the 50% in the output. So how long it takes that 50% to 50% the transition. Suppose the input is making transition from low to high, and depends on the output may go from low to high or high to low, depends on the logic. So if it is going, output is also making the transition from low to high, in that sense 0.5 to 0.5 from input to the output, it takes that is the TPLH. So in the case, suppose input is if we take the other cases of this propagation delay, so when the input goes from L to H, the output may also make transition from L to H, that is TPLH. So output is changing from low to high. When the input makes, suppose L to H, but the output make from H to L, depends on the logic. So this is called the TPHL. So what is the transition of the output, whether it is going from low to high or high to low, because of the input change, either it may be LH or HL. So the other condition may arise if input is high, going from high to low transition, the output may from L to H. In that case also it is TPLH. Whereas input makes H to L transition, and then the output may go from H to L transition as well. So in that case it is H to L. So whatever the input change from L to high or high to low, the output transition low to high or high to low is that it makes the propagation delay TPLH or TPHL. So if we take the input, suppose this is the input, 0.5 of the time maximum value, we mark it here to define this. And the output, suppose, is transiting from this low to high or high to low in this fashion, the rise time, and this is 0.5 of the input where it makes the transition from this is 0 to 1 and here 1 to 0. So it's not a straight line like 0 to 1, you can see the difference, there is a slope involved in it. And then this is going to be the output, which is also having not a exact 0 to 1 or 1 to 0. So there is a slope, there is a change in these cases also. The 0.1 which is marked over here, 0.5, 0.9, okay, this is 1 Vmax. So the 0.5 to 0.5, this is TPLH, where output is going from low to high irrespective of this thing. So this is TPLH. Propagation delay low to high, and when this 0.5, the input to the 0.5 here, where the output makes the transition from high to low, that is 0.5, that is TPHL. Propagation delay is of LH and HL, that depends on the output one. So raise time, what we said as is the 0.1% of the 0.1 maximum 0.1 of the maximum value, or 10% of the maximum value to the 0.9 Vmax, or 90% of the maximum value. So this is TR. And we have this similarly fall time, that is from 0.9 Vmax to 0.1 Vmax in the falling edge, that is when the output transition from 1 to 0. This is falling time. This is 90% to 10%. So this can be these timing parameters involved in the circuits. The combinational circuit can be understood from that. So from that, suppose we have the combinational circuit in which we have the gate, not gate, and AND gate. The propagation delay is specified. Simply it is not a propagation delay of 3 or 2, and here TPLH, the specification can be TPLH and TPHL. So in the nanoseconds, this is 3 and 2. So in suppose this is a circuit in which we have 3 nanoseconds of a low to high transition, where the output of this NOT gates make a transition from low to high. So all these NOT gates, and when they make transition from high to low at the output, okay, so then this is 2 nanoseconds. So that's the meaning of the specification of this. Here an AND gate, which is again has the LH, when the output of the AND gate makes low to high transition, it is 5. So the 5 nanosecond, that is from the input 50% to the output 50%, that is here again. And this is also high to low transition is 3 nanoseconds. So this way we can when input is making from 0 to 1 transition, what is the output transitions, and where this output will be can be easily calculated in the. So the timing is involved in this circuit. So so far we have seen the combinational circuit, which doesn't include any propagation delays. So now maybe in very long codes, we will when we do the synthesis, these parts of this can be seen, what is the technology specific delays, propagation delays for each of them. So apart from that, we can also specify a particular delay for the gates when we develop this very long modules. So the worst case propagation delay, for a circuit from input to output, what should be the how it is considered. Okay, so suppose a circuit which has two here cascaded circuit, combinational circuits, which has here, which have these two things, where two circuits, one is having 2 nanoseconds and another one is having 4 nanoseconds. So in that case, so from this is considering the direction as input to output here. In that case, what should be the propagation delay for this circuit? Okay, so here is 2 and 4. This gives 2 plus 4, it is 6 is the propagation delay, 6 nanoseconds. When the cascaded connection, it is added from input to output. Whereas if we take the second case here, this is having 2 parallel combinational circuit, and one is the one common for the 2. So from input to output, you take all the combinations from input to output. Here is the one path and another one, this is the second path. So 3 plus 5, this is one thing, and then 2 plus 5, that is 7. So here one path takes 8 nanoseconds and other takes 7 nanoseconds. The maximum of is the propagation delay, actually 8 will be here. So here again, in this case, you have the multiple paths. If you identify, one from output to input also goes through the direction 6 plus 3, which is 9 we can take, and 3 plus 5 also this, and then there is another path from 2 to 2 plus 5. So maximum of this would be 9. So the propagation delay should be taken as the worst case delay, should be the maximum of all the paths from input to output cases. So which identifies the worst case propagation delay, also the critical path of the timing delay of the critical path. The critical path is actually the longest path between the input and output, through the circuits, the logics which has been designed in this case. So for the adder, multipliers and those examples what we had done, from them we can calculate the critical path for with the logic circuit also. So worst case propagation delay is the maximum delay which is involved in the in a path between input to output. So the delays of the sequential elements, so these are combinational ones. So whereas in the sequential elements plays an important thing here, the delays delays which are pertaining to the sequential elements are something different from the combinational circuits. And then one is the setup time, which was mentioned. So setup time is the time for which this, in the case of flip flops, if we take that clock edge, we have a clock edge passage of the clock, and the data change, data D input of the flip flop. So there should be a minimum time allowed for which the data should not change before the clock edge or clock edge become active, or the clock becomes active. In that case, this is the setup time of the flip flop. So if that should not, must not change in the data, should be stable in that duration. So that is the setup time. And similarly, hold time after the flip flop clock edge, the passage of the clock is arrived, then how much time that the data should be stable again. Okay, so this is setup time and this hold time. And this latches, it is slightly the different definition, that in which it, instead of a clock edge, even the clock has become one active, the data how much time the data should not be changing, that is stable. And after the clock has become inactive, how much time that clock, the data should be remain stable. So setup time and hold time is the important parameters here in the sequential elements, which needs to be taken care in the design as well. So the propagation delay, as we have seen in the combinational circuit TP-LH and TP-HL, here for a sequential element, there is a, suppose it's a flip flop or the latch, clock to Q delay is also there for TP-LH propagation delay, and D to Q delay also is the so data to Q delay or clock to Q delay. These are part of the propagation delays of the sequential element. So for example, if we take a flip flop, so this is this data which is sensed at the clock edge. Okay, so the data to clock, there is a delay D to C, and the clock to Q, after this clock has been clock samples the data, and then this is clock to Q delay, how long it takes D to assign in the Q. So that is a clock to Q delay. So in the flip flop, it's an edge sensitive behavior. So in that case, with respect to the clock edge, the D and Q, what are the delays involved in it? So this is related to the DTDC and the clock to Q delay. So whereas in the latches, you see D to C, there is no clock. Clock is level sensitive, and this is enable one. If it's level sensitive, and that's the D to clock or the D to enable, how much is the time, that is D to C, it is there as in the flip flop. But also clock to Q delay, yes, that is when level becomes 1, C becomes 1, that how much time that data changes, data is taking to be assigned in the Q. So that is clock to Q delay. Whereas the other parameter which is involved in the latch is D to Q delay. Okay, so when the D is changing during the clock is 1, okay, so that is level sensitive, that time, that the how much time it takes, that is D to Q delay also is involved. So the latch has the 3 parameters: DC, TDC, T clock to Q, data to clock, and the clock to Q, and then data to Q also. So there are 3 parameters involved in the latch. So if we try to understand those parameters here, the latch and flip flop. So considering this D flip flop positive edge triggered, okay. So here what are the clock, we can see here, this clock is given with a slope in this diagram, and this is the clock edge which is considered as 50%, okay. as a reference point, and similarly when it is going from high to low, the transition, the 50% is taken as the reference here. And then if take this is the clock width, which is shown as TW. Okay, so the similarly here also the clock, this is shown as TW, this is for latch. Yeah, the clocks of the two flip flop and latch. This clock here we mean this, that's actually the level sensitive one. So the setup time and hold time for the flip flops, we said the data is changing over here. So here from this, the setup time of this flip flop is from here to here. Okay, so in this duration the data should remain stable. Okay, so that is a data change can occur here in this, away from the clock edge, it should not be near the clock edge. Okay, so that is the setup time. There will be a window for the flip flops, that setup time and hold time, so that in that duration that data should not be changing. So similarly active edge of the clock is considered here, and this hold time is TH, where after this clock has become active and what is the time at which data is changing. Here this is TH. Okay, so this is the hold time for the flip flop, setup time and hold time. So if we consider the setup time and hold time of the latch, so considering this, the data is changing over here, but the in the clock will be active till this point. So the setup time is this duration for the latch. So it is different for the case of, it is up to the clock edge, whereas here it is going up to the neg edge of, or it become inactive. And hold time after it becomes inactive, where the data changes. So the allowed change is the hold time. So the data should be stable, not changing, that is TH, during which data should not be changing. So the setup time, hold time, duration in which data to be stable, that's the window for which the data is stable. So here also TH, which is shown from this point to this point, the TH for the latch as well as the flip flop. And if we consider the low to high transition, so here this D is changing from low to high, so that is sampled at clock edge, and after, because this would be though the data is changing before this, so that will be reflected only, the clock can sense at only the sample at this point. So the this one will be transferred to Q with a delay. So the data which is changed before the sample so setup time can be reflected only after the clock edge, passage of the clock. So this is from the passage of the clock to the Q, this delay is the TPLH delay, because here low to high transition of the output. And the latch, when we take this TPLH, here this is the point of the clock is active. Okay, active, and that is the data changes, though data is changing here, that can be, when data will be sensed, the data change will be sensed only when the clock or enable become 1 here. So that is from here to Q, that is TPLH, how much time it takes for the data change to be reflected in Q. So this is for latch, though the TPLH difference is not visible here in this case. So you can say this is 1 to level, from the level of a clock equal to 1. Here is the clock edge, is a difference here, the flip flop and the latches. So in parameters involved are setup time, hold time, and then the TPLH. If suppose due to this, this would have been changing from high to low, then that is called the TPHL. Similarly here also. So the setup time and hold times in that. So if this is a clock transition, and if you see, suppose the data is changing like this, the data should not be allowed to change during the setup time, T setup time, also T hold time window. There is a window in between. So in case of flip flops, so this will, the setup time will be extending for the till the inactive edge of the clock for the latches, as we have seen in the previous diagram. Here, if the data is suppose changing over here, okay, that exactly at the clock edge, So what is the impact on this would be, so the data which is shown over here, this is the reflection of won't be proper, it won't be going to low to high. Okay, so further the change, so here is the next one, and which is showing the better output, and if the change is away from the clock edge, the third one is this better output, and the fourth one is the still better output you get. So if the data changes before the setup time, away from the clock edge, that would give them better and better output. Okay, so this data should be stable near in the setup time duration. Similarly, the hold time also will be seen that way. So considering these the setup time, hold time, and then propagation delays of the flip flop and latches. So we have this sequential circuit in this. If you consider them flip flops in the sequential circuit, we can consider the common sequential circuit which we had done in the state machine as well. So the input forming logic or the next state logic here, which is given the output to the state memory or the flip flops, and by taking this input, and that overall circuit output is here, and output logic also taking the current state and the of the flip flops, whatever the status is, and input from this next state to output can be one. Also it can go from here, or it can go from the input to directly to output as well. Okay. So the feedback diagram which is shown over here, this is from the output to the current state to the again going back to this state memory. So from this circuit, which can be, see, when the timing parameters shown over here, what are the timing parameters involved in this sequential circuits. So TIA is the delay from input to output logic. So when the input is applied to the output logic, what is the time involved? That is also, because those are combinational circuits in the input or next state logic and output logic. And TIF is the input delay from the input to the flip flops. When the input is applied here, the combinational logic is going to the flip flops. So TIF, that is another delay from input to the flip flops. And then delay from flip flop outputs to output. So the current state, the flip flop outputs to the output logic, that is TFO, F and O, and FF is the flip flop output to flip flop input. So it has a feedback also, flip flop output to flip flop input. So that is FF. Also clock to Q delays of flip flops. So when the clock here we see clock to Q delays, the propagation, each flip flop can have the clock to Q delay, and also the setup time. Whenever there is a flip flop and latches, that then setup time is involved, and hold time also of the flip flops. Clock delay, that is clock to reach all flip flops. There will be a global clock in from that that should reach to the each flip flop. So there may be a delay between them. The clock delay is the clock time between the global clock to the clock obtained by the each flip flop. So that is clock delay. Also global setup time, TSU, the parameters involved. Global hold time, for this it is not the setup time and hold time of the flip flop and the latches, it is just flip flop including the flip flop and the latches. This global setup time and the global hold time. Also the maximum clock frequency, what is the clock frequency in for this particular circuit is required, and the clock skew, what is the clock skew, is they involved in it or not. So that means all the flip flops are seeing the clock at the same time, or there is a delay between this. So that is called the clock skew. And how much is the clock which is required for this whole circuit. Global hold time, TH, global setup time, for the whole circuit, and for the whole this is also hold time for the whole circuit. So we can take this latch and flip flop timings, and then we'll move on to this global setup time and to the hold time cases. So here we have the clock which is shown over in this here. The data is changing in these places. You can see this data changes some places randomly put it. And if we take the flip flop, so setup time we said where the data change and the clock edge, passage of the clock, this is setup time, and the whole time from here to again this data change here. Okay, so that is the whole time. So this can be anywhere in between here. Actually this should be near the clock edge. So this is the hold time. For the clock to Q delay, this change which is sensed here is passed on to this one would be given only to Q, that is clock to Q delay. This is the delay which is involved in this clock to Q delay. So setup time, hold time, and the clock to Q delay for the flip flops, that is same as what we had seen. But whereas latches in this clock edge, if you see, this is an enable of the clock 1 here. So the data change, and that would be here after this becomes 1 is reflected here. Okay, so this is the after this clock becomes 1. So the clock to Q delay is this, yes, and setup time is from here to the negative edge of the clock. Instead of the negative, instead of this, you have the say here the clock is inactive at this duration. So setup time, this setup time and this setup time, there is a difference here. And the hold time, so after it becomes inactive, how much time it takes for the data load to be stable. So that is TH. This also can be seen over here, which involves D to Q and C to Q also. So here the one which is the clock change is observed clock change, and it's clock to Q. Suppose data change in that in between. Okay, so here the data change is when after the clock edge has become 1. Okay, so that can be reflected in the, but that is nothing to do with the case of flip flop, because it will be taken care, or it would be sampled at the next passage of the clock. Whereas latches would if there is any change during the level equal to 1, then that would be reflected. Okay, so this data change to here, this is, you can see, this is clock to Q delay. Okay, this one is clock to Q delay as in this here, but we have to understand from here this D, data to Q, this data is changing the Q at this point. So the data Q is here only, not at the same time. So if it is changing immediately, then it will be a data to Q. So setup time from here, data change to the, this is same as the previous here, and the whole time that after which data is changing, this is fine. So only is the, if the data is changing from here and then data is sensed, and that is will be clock to Q, or the data to Q will be, data change will be reflected at the Q after this change is here. So that is data change. Here it is the data change, this is D to Q. You can see the difference here. So this is for latches and the latch and flip flop. Setup time, hold time, and the clock to Q, D to Q delays. So considering the whole synchronous circuit in which that global setup time and hold time, where the clock at the source. Okay, so in the synchronous circuit, synchronous sequential circuits, or sequential elements which is of the sequential circuits having the flip flop, latches, and combinational circuits as well. So in this setup time and hold time, this is the clock at the source, that is clock source, and the same clock can be given to the flip flops. Okay, so what is the difference if there is any delay between these two? So we can observe this is the clock at the source and this is the clock at the flip flop. So in that case, there is a delay between this two clocks, that is clock delay, TCV. Right? So but the flip flop sees only this clock, that is so with the delay from the global clock. So the global setup time and the global hold time is valid with respect to this clock, whereas this setup time and hold time for this, as usual in the case of the flip flops, as we have seen in the previous diagrams also. So we see this clock and the data, this is X input, the input to the circuit, and this is D input. Okay, so D input to the flip flop has to be something to do with this clock, that is setup time, as we said, this is D flip flop, and the whole time of this also here, from here to here, this whole time is valid in this diagram, whole time. So now this is setup time and whole time of the flip flop, the small ones, and input is changing somewhere at this point, and in here also input is changing. So when the input this is not the flip-flop input, this is the circuit input. So, and the input is changing. So, here this input change is seen by the global clock, okay, global clock here, that is global setup time, okay. And then the same date input is changing after in this with respect to this clock over here, that is a global hold time, okay. Global hold, and there is a difference between this setup global setup time and the setup time of the flip flop. Similarly, global hold time and the hold time of the flip flop. So, there is a clock delay involved in it. So, this TIF input to flip flop. So, if from the input change, it takes some time to get into the D. So, that is the time TIN. So, depends on the combinational logic, the next state logic, which is combinational, the TIF proportional to the logic gates. So, again here this is again the TIF, the input change will be reflected to D input, this is again TIF. So, if this is the case, what is the global setup time? So, global setup time and global hold time are this. So, this setup time here, setup time, which is that's the maximum with respect to the this clock and data change. So, and the input flip flop, this input to flip flop delay, that is maximum, and if there is any clock delay, that is should be subtracted from it. So, this adding all of these two and subtract this clock delay would be the setup time. So, minimum it is, and hold time similarly, this TH, which involves this TH of the flip flop minus this input to flip flop delay, this needs to be subtracted, and the added TC max, that is TH from here. So, the global setup and hold time can be obtained from the setup time and hold time of the flip flops, and if you know the IF input to flip flop delay and clock delay, then this can be found. So, the if considering the same circuit which is having the combinational logic and the flip flop, the output logic is not shown over here. So, the interaction between the combinational logic, we can consider this feedback from Qj to here, Qi to here. There are two flip flops here, Ti, Di, and inputs are Dj. So, the clock which is this jth flip flop is obtaining is Ckj, and here is Cky. Okay. So, the flip flop to flip flop from here to here, that is involved, the time which goes into this. So, the output from here gets into the combination logic and go to the next flip flop. So, that time is this flip flop to flip flop in delay. So, if you consider this Cky, that is the lowest one, this flip flop, suppose this is ith flip flop and this is jth one. So, Cky, the clock over here, which is given, and whose output, suppose change in the data, previous this data, it has changed the data output here, okay. So, that is clock to Q delay of this is known, clock to Q delay, this is from here to here, this clock to Q delay, and then this output is reflected in the input of the DJ, which is flip flop to flip flop delay again. And then after coming here, this signal, that there is a setup time involved for this flip flop as well. So, that is TSU, that is belong to the J flip flop. So, your clock should be, so these three things should be involved in the clock period. So, the clock which is decided for this particular circuit should be at least greater than this clock to Q delay of this flip flop plus flip flop to flip flop time, that delay, plus the setup time of the second flip flop. So, it should be at least minimum of this. So, that clock frequency of this circuit can be decided 1 by T clock is the. So, this is the total clock time duration for this. So, this is how the maximum clock frequency is decided by the circuit. So, clock to Q delay of this and the flip top to flip flop and setup time. So, this in this, assuming that this clock does not have any delay, or both the flip flops are seeing the clock at the same time, no clock skew here. So, the clock the expression what we obtained is clock to Q flip flop and setup time. Then if this, suppose the clock we choose, the clock has avoiding this setup time or of the next one, what here, then it would lead to second flip flop, then it would lead to setup time violation. So, setup time violation can be avoided by faster flip flops, and flip-flops having this, and then faster gates as well, because FF is also involved in that. And or we choose this lower clock should be lengthier, so that these operations can be completed in that duration, so that timing violations will not occur. So in the synthesis, after synthesis of the Verilog module, when we get into the timing analysis, this would throw an error of timing violation of setup time or hold time, and the critical path, identification of critical path, and so on. So the clock skew is that difference in time between the triggering edges seen at different flip-flops. Okay, so that the same time the clocks should be seen by the flip-flops, all the flip-flops. Then the clock skew is 0. So coming to the clock, the same circuit, suppose this clock is seeing the clock at some time, and there is a skew between the next flip-flop clock. So assuming that CkI, this is the one, and Ckj, there is a clock skew, like the clock delay between the flip-flop and the global clock. So between these two flip-flops there is a delay. In that case, that this is called the skew. That skew is mentioned over here, I and j. And if the jth flip-flop, suppose this is the one here, whatever the change which was sensing at this point, it is passing to q. So that is clock to q delay, TCQ. And then after this q, which is getting into the flip-flop input, TFF. Okay, that is to this flip-flop DI. Here, this is flip-flop to flip-flop input. This back to here even, and then this setup time, the setup time of DIG. So whether you move it through this way to here, considering this setup time over here, that is from DI to the clock of this clock, how much time, that is the setup time. So this clock duration is this. Now how the clock duration is decided? This is skew plus this clock to Q delay of the jth flip-flop, clock to Q delay of the j flip-flop, and flip-flop to flip-flop delay here the time, and then setup time of the other one. So this is maximums of the clock delay. When there is a skew, then this skew term should be added. What should be the maximum skew? That also should be taken care when decide the maximum clock for the design. So for the latches, how it gets differ this particular case. So considering them as latches here instead of this clock edge, this is latch. Okay, so it's not a flip-flop, this is latch. Okay, so that's going to be an enable only. So similarly here, this diagram, we have only latch, these latches. I and K are suppose latches. Okay, in that case, the Ki and Kj, whose clock has been given here, the clock skew is also there, and the width of the jth clock here, this TW plays a role instead of the clock edge. So TW is the width of this jth clock, and the data which is changing over during the clock 1 of jth here, this is data change. Okay, and the inactive clock this time, so this is setup time, this is setup time of j. Okay, and this data change is reflecting in Q for D to Q, because D is changing after this clock has become 1. So D to Q delay is involved, and after this Q, it fed back to this latch, so TFF, and then TFF, in the sense this is the feedback here, this latch to this latch, so the FF, and then setup time of this particular latch. Again, this is related to the here KJ, inactive, the setup time of DI. Okay, so including all of them, it includes all of them. So skew, which is over here, plus the TW minus this setup time, that is this minimum over this time, this is this time here, which is mentioned also, and then D to Q, whatever the D to Q. If you just go through over here, this side time and this time, and then D to Q, this is the D to Q, and then TFF, and then the setup time, whatever is for the applicable to the next latch. So setup time. So these should be included in the clock. So the clock should be at least greater than or equal to all the sum of all these times, where the change can be observed instead of C to Q, there is a possibility of D to Q. So this, and the width TW to the setup time. So this needs to be added also in the case of latches. So it includes Q, TW minus TSU, DQ, TFF and setup time. So this is with latches. If this is if the circuit that has latches, then the clock, how to decide the clock frequency. So this is giving the maximum clock frequency. 1 by T clock will give the maximum clock frequency for this circuit. So with this we have seen the timing analysis of the combinational and the sequential circuit. At least the timing parameters involved in these two combinational and sequential circuits. So how to decide the clock frequency of a sequential circuit when it consists of combinational logic, the input and output forming logic, as well as the state memory on the with the flip flops or latches. Also the propagation delays, TPLH and TPHL in case of combinational, and TPLH and TPHL, the meaning of TPLH and TPHL in case of flip flops, the output may go from low to high or high to low, that is depending on the clock and the data in which that. So these parameters will be analyzed in the timing analysis when we do in the for the FPGA using this simulator. So after this coding module code, and then coded module is simulated and checked for functionality. After that synthesis process is done. So after synthesis you get to know what the synthesizer output is, what is the technology schematic, and the technology schematic then next go to the real-time implementation wherein the timing analysis is checked for the design. So after checking that design, and the bit stream will be generated. So this information would be helpful to when you do the real-time implementation of the code, or compiling it for real-time implementation. So what is the critical path involved? What is these delays involved in the design what you had modeled? So this can be understood from the parameters we have studied so far. So thank you so much.